Okay, in this lecture we're going to cover the next part of the section 3.3 material, which will make use of Cramer's rule to give us a formula for the inverse of a non-singular square matrix. So let's suppose that we're interested in determining the inverse of some n by n matrix, let's call it A. Now we know that the jth column of A inverse would be a vector x that satisfies the equation A times x is equal to E sub j, where E sub j is the jth column of the identity matrix. We can see that here from our equation. If we were to solve this equation for x, we would multiply both sides on the left by A inverse. So we would have x is A inverse times the vector E sub j, which would be the jth column of A inverse. So we might denote that A inverse, say, sub j. Now, the ith entry of this vector x would be the ij entry of A inverse. So the ith entry in the jth row would be the ij entry of A inverse. But by Cramer's rule, the ij entry of A inverse would be given by x sub I is the ratio of the determinant of A sub I of Ej. So recall from Cramer's rule, the ith component of this solution vector x would be given by the ratio of the determinant of our matrix A with the ith column replaced by whatever vector is on the right-hand side, in this case E sub j, divided by the determinant of the coefficient matrix A, which is non-zero as long as A is invertible. So if we make use of a cofactor expansion down column I of the matrix A sub I of Ej, so here column I is exactly the vector Ej, then we find the determinant of A sub I of Ej is negative 1 to the I plus j power times the determinant of A sub ji, which is exactly the definition of the cofactor of A, the ji cofactor of the matrix A. So this ijth entry of A inverse, so let's recall what we're after, is an arbitrary ij entry of the inverse matrix, is the following expression. And this determinant for our numerator we've just shown is the ji cofactor of the matrix A. So we take our ji cofactor and then we're dividing by the determinant of that matrix A. So our general formula for A inverse is the matrix whose ijth entry is the ji cofactor of A divided by the determinant. So along the first row of the inverse matrix, we have the 1, 1, 2, 1 up through n1 cofactors. In the second row, we have the 1, 2, 2, 2 up through n2 cofactors, and so on. And each of those cofactors was being divided by the determinant of A, so that factor of 1 over the determinant of A, we can factor out from each entry in our matrix, and therefore factor out from the matrix itself. Now, this matrix, which contains all of the cofactors, is referred to as the adjoint of the matrix A, or in your textbook, I believe they use the adjugate of A, and it is denoted as follows: A dj of A. All right. So this results in the following result. Theorem 3.8 from your textbook is an inverse formula for an invertible matrix. So if A is an invertible square matrix, then the inverse is given by 1 over the determinant of the matrix times the adjoint of A. All right. So let's look at an example making use of this new formula for an inverse matrix. So here we are asked to compute the adjoint for the following 3x3 matrix A, and then make use of this new result, theorem 3.8, to find an inverse of the matrix. So to find our adjoint, we need to find each of the cofactors for this matrix. So let's start there. Here, the cofactors of A are as follows. So since we've got a 3x3 matrix, we'll have 9 cofactors altogether. The 1, 1 cofactor is the positive determinant of the matrix we get by deleting the first row, first column. So we have the matrix 2, 1, 1, 1. And the determinant of that matrix is 2 minus 1, or 1. The 1, 2 cofactor is the negative of the determinant of the matrix negative 2, 1, 0, 1, which gives us the negative of negative 2, so we're left with a positive 2. And our 1, 3 cofactor is the positive determinant of the matrix negative 2, 2, 0, 1, which leaves us with a negative 2. Now moving to our second row for cofactors, we have the 2, 1 cofactor is the negative determinant of the matrix 1, 3, 1, 1 when we delete the second row, first column, which leaves us with the negative of 1 minus 3, so positive 2. Our 2, 2 cofactor is the positive determinant of 1, 3, 0, 1, which leaves us with 1. And our 2, 3 cofactor is the negative determinant of the matrix 1, 1, 0, 1, which gives us a negative 1. And for our last row of cofactors, the 3, 1 cofactor is the positive determinant of 1, 3, 2, 1. Which would be 1 minus 6, or negative 5. The 3, 2 cofactor is the negative determinant of 1, 3, negative 2, 1, which leaves us with a positive 5. So we've got 1 minus the, not 5. So our determinant is 1 minus the negative 6, so 7, so we're left with a negative 7 there. And for our 3, 3 cofactor, we have the positive determinant of 1, 1, negative 2, 2, which leaves us with 2 minus the negative 2, or positive 4. All right. So the adjoint or adjugate of the matrix A is adjoint A, which would be the matrix where the ijth entry is the ji cofactor of the matrix A. So our cofactors that we found along the first row will become the first column of the adjoint. So here our first column will be 1, 2, negative 2. The entries that we found for the cofactors along the second row of A become the second column of the adjoint. So we have a 2, 1, and -1. And the cofactors that we found for the third row of A become the entries in the third column of the adjoint. So here, -5, -7, and a +4. All right. So we found our adjoint. That was the first part of this problem. And the second part is to use our theorem 3.8 to find the inverse of this matrix. So we still need to find the determinant of A in order to apply that theorem. So let's take a look at it here. We have, for the determinant of A, we can make use of a cofactor expansion, say down the first column, since we have a 0 entry in that first column, or maybe along the third row. It doesn't matter. So I'm going to use a cofactor expansion down our first column. So we'll have a +1 times the determinant of 2, 1, 1, 1, minus a -2 gives me +2 times the determinant of 1, 3, 1, 1, plus 0. So let's see what we're left with. We have 1 times 2 minus 1 is 1. And then +2 times 1 minus 3 is -2. So that leaves us with a -4. And our determinant of the matrix A is -3. So making use of theorem 3.8, we know that A inverse is found by taking 1 over the determinant of A times the adjoint of A. So our 1 over the determinant of A, factor out in front, is a -1/3, which we're multiplying by the adjoint matrix, which we've found here. So multiplying each entry by a -1/3, we have our inverse. So in this case, -1/3, -2/3, +5/3, -2/3, -1/3, -7/3, and, +7/3. And then our last row, we've got a +2/3, +1/3, -4/3. All right. So this would be our inverse matrix, making use of that adjoint formula. So we see here that, at least in the case of a 3x3 matrix, this theorem is not a particularly efficient way to find the inverse, but it does hold for any size square matrix. And so in some cases, depending on the form of A, if we recognize that several of our cofactors might be 0, then we can make use of this adjoint formula to easily find an inverse. And it does give us a closed formula for the inverse of any square invertible matrix.